let's consider now a shell. And our shell has inner radius A and outer radius B. This is a cylindrical shell where the current, this is a cross-section, and our current is out of the plane of the figure. Now, we have in this problem 1, 2, 3 regions. And so now we have to choose Ampere's law for all 3 regions. And I'm going to draw for my region 1, that will be the easy one. So this is 0 less than or equal to R less than or equal to A. I'll do Ampere's law. Now again, because of the direction of J, I don't know, but just suppose I assume that B fields are circles like that. And so I'm going to draw my circulation direction. I pick an Amperian loop, radius R. I orient the loop that way. My n hat, r hat is out of the plane of the figure. And so as before, B times 2 pi r. But how much enclosed current is there here? There's 0 enclosed current. So this side is 0. And so we conclude that inside, this is the shell. This is vacuum. And so inside the shell, there's no B field. This is the cylindrical version of Gauss's law for a spherical distribution of charge. Now, it's in the shell that things are a little tricky. So let's draw a blow-up of that shell. We'll make it big. And now J in the shell is coming out. This is radius A. This is radius B. And now I need to apply Ampere's law. B dot ds equals through the shell, well, not through the shell, but through our Amperian loop of J dot n hat dA. So now I'm going to do what I did before for the solid wire. I'm going to choose my Amperian loop first here, circulation direction theta hat, n hat right-hand rule out of the board, radius r. Now, the current enclosed, I'll just start to shade it in a little bit here. This goes all the way around. So how am I going to calculate that current? As before, I'm going to choose a shell of thickness dr prime. A little hard to draw this. Well, so the thickness is dr prime, and the radius of that shell is r prime. And I'll calculate first the current in this small area element, where dA prime we've seen before, that I can write that as that. The 2 pi is the theta integral. And so I get B times 2 pi r equals mu naught. And now I'm integrating J times 2 pi r prime dr prime. And here, we didn't say this, but J is uniform. So what am I integrating r prime from? The biggest mistake people will make will be to say from 0 out to B. But remember, J is 0 in the vacuum. So the only place where J is non-zero is when we go from A. And our Amperian loop only goes out to R, so I'm not interested in the current outside the Amperian loop. This is R. And I think that's the tricky one. So we get B times 2 pi r equals mu naught J, 2 pi integral of r prime dr prime squared is r prime squared over 2, evaluated between the endpoints. And so I can conclude that B times 2 pi r equals mu naught J. The 2's cancel, the pi, and I get B squared. Oops. See, I made that mistake. The upper limit is just r prime equals r. So that's not B squared, but that is r squared minus a squared. And so what I get is that B is mu naught J over 2, r squared minus a squared divided by r theta hat. And now I think if you want to ask what is the total current through this wire, then this integral, the only difference here we'll be integrating from r prime equals a to r prime equals b of j times 2 pi r prime dr prime. And so the total current is 2 pi j times b squared minus a squared is I. And let's just, with a factor of 2, I was looking for my factor of 2. The integral is r prime dr prime, so that's r squared over 2. And so I could also write this as mu naught I. Let's divide by 2. Let's take r squared minus a squared, divide by b squared minus a squared, because I substitute in for that, and I have a 1 over r theta hat. So what I'm seeing here is this factor here, I times this. This is the ratio of the area of my Amperian of this area to the big area here, and that's the fraction of the current that's enclosed. And so that is my result for the magnetic field. And let's just check our results. And that's the field inside this shell.